Okay, in this problem we have another potential energy problem. So I have a charge on the y-axis at the origin. So I've got this positive charge here, and and the charge moves to some position here at say negative 15 and 32, and these are in centimeters. So that positive charge moves here, and it also tells me that this charge is in a field directed upwards. So I'm thinking it's a constant field directed upwards. And now I know a positive charge is going to want to move with the field. So I like to think of how would I create a field like this. I might have a very distant positive charge and a negative charge here, and my field lines are going to look like that. And so if I think about a positive charge is going to want to move towards the negative field, so it's going to want to move with the electric field. And now if I think about potential energy, I'm going to have more potential energy if I'm close to this positive charge. And I like to think about that kind of like gravity. If I were to drop something off of a building, it's going to want to fall to the earth. So this is like the same idea that if I put a positive charge here, it's going to want to go away from this positive towards the negative. So when I take this charge and it goes to this position here, it's going against the field, and so I'm increasing potential energy, meaning that I would have to go against this field and then hold it, and then if I were to let it go, it's going to fly that way. So I have more potential energy here than I do here, so I'm going to have an increase in potential energy, which means I'm going to have a positive value. The other thing is I know that my potential energy is going to be, my potential energy formula is equal to Q times E times y2 minus y1. And so, and like I said, it's going to be positive. So I'm not going to worry about the sign of this. I just know it's going to be positive. So this is going to equal the charge, which is 5.4 times 10 to the minus 6 coulombs, times the E field, which is 327 newtons per coulomb, and then times, and then multiplied by that 0.032 meters. And so when I multiply that out, I find that the potential energy equals that answer here of 5.65 times 10 to the minus 4. And now does this, let me think, this should be joules. So if I think about my units, I have, this should be newtons per coulomb here. Okay, so I have coulombs times newtons per coulomb times meters. So I end up with Newton meter, and a Newton meter is a joule, unit of energy. Okay, now for part B is asking through what potential difference did the charge move? So to find the potential difference, I need to find the potential difference, I need to take the potential energy divided by the charge. So remember that potential difference is potential energy per charge. So if I have a charge, this was the charge that was involved, so I need to divide by that to get the energy per charge. So I'm going to have this PE, so 5.65 times 10 to the minus 4 joules divided by my charge, which is 5.4 times 10 to the minus 6 coulombs. And so when I multiply that out, I get that number of 105. So I get 105. And so I see here my units, joule per cool is a volt.